Hi there, Mr. Leonard here. Today we're going to be talking about the periodic table in this podcast. And you're saying to yourself, well, it looks like there's a star and a planet here. Well, that's because I want to share something with you that is directly related to the periodic table of elements. Let's start by taking a look at this star, which is one of our closest stars to us. It's called Alpha Centauri B, 4.3 light years away, which means if we could travel to it at the speed of light, which is really, really fast, 186,000 miles per second, it would take us 4.3 years. So it's kind of unimaginable to go there. But what we're finding near these stars are planets. They call these exoplanets. They're trying to search for planets that are like Earth, search for planets that could possibly host life. What they do is they measure the light that is bouncing off the surface of these planets, and they analyze it, and they could figure out exactly what it's made of. So maybe they find water, or maybe they find methane, or maybe they find carbon dioxide, or maybe they find oxygen. If they find all four of these, there's a really good chance that it could support life as we know it. So they're looking at these and analyzing these based upon light and figuring out what elements are there. And that's something that's really, really neat, and that's what they're doing. They're also taking the Hubble telescope, which you've probably heard of before. This is just a regular telescope, but they're measuring the light that's coming from stars, and they're also figuring out what they're made of. So this particular configuration is related to one particular element, and it kind of works like a chemical fingerprint. You think of a crime scene. The FBI or the police or whatever, they're looking for fingerprints to figure out who did it. It's unique. Well, each chemical has its own fingerprint that would be found on our visible spectrum, the light that we can see, the colors of the rainbow. And what they found is that sometimes this spacing that you see here, like this, gets shifted to the red side. They call that a red shift. If it's shifted to the red side, it means that it's moving away from us. If it's shifted to the blue side, it means that it's moving towards us. And this is really neat because in the 1920s, there was a guy named Edwin Hubble who found that almost every star and galaxy in the universe are moving away from us. And that helped to support something that we call the Big Bang Theory, which you've probably heard about. And without our understanding of the periodic table and the elements on them, we would have never been able to figure that out. So this is something that's really neat, cool to understand. If you ever get a chance to take an astronomy class, take it. You'll get a full understanding how this works. It's really cool stuff. Now, we can't owe any of these great discoveries, the new planets, the stars, the galaxies, unless we have a good understanding of our periodic table. So this is what we are going to focus on for today. Okay, so to get started, what we're going to do is first take a look at this word. So periodic, well, it has the word period in it. We think of a period like a period of time. We have Earth revolving around the sun every 365 days. It marks a brand new year for us. That is a period of time. All right. Now, we also have periods on here, a predictable pattern where properties can be figured out based upon its position on the table. So they call them periodic trends. So this is our periodic table of elements. Well, the periods are really the rows that are going across. I'm going to start by labeling this. So you're going to need some colored pencils or some highlighters or something here to distinguish between these different groups that we're eventually going to be labeling. So if you need to pause the video at any point, feel free to. I'm going to start by numbering the periods. Now there's 7 of them. And you might say, well, it looks like there's 2 more down here. Well, these 2 groups are really shoved up into that section. The reason why they're not is because the periodic table would be really long and it wouldn't fit on a piece of paper or a poster, and it wouldn't really be practical. So they've kind of taken these ones and separated them from the group. So we've done that. Now what we're going to do is label these columns. The columns are called groups. And we're just going to number them as we go across. So very, very simple. Each one of these groups is very similar to one another. You can think of them like families. So for example, if we take a look at this element here, this element is sodium from this first group, which we call the alkaline metals. Please label that. So the alkaline metals are all similar in that they're all highly reactive. And also, they all like to give away one electron to become stable or happy. So all of these things are very, very similar. If you have some free time, take a look at any of these metals. By the way, they become increasingly more reactive as we go further down this alkali group. So if you look up something like cesium or francium on YouTube, you'll see some really cool videos that are out there. So if you get a chance, check that out. So that's that group. The second group is related to this element right here, beryllium, or beryllium is part of those, and this is the alkaline group. So these are the alkaline earth metals. The alkaline earth metals are all very similar as well. These all like to give away 2 electrons. You've probably heard of things like magnesium and calcium. Very, very important for your health, especially calcium with your bone structure. So these are all really important elements. The next group that we're going to label is way over on this side. These are the noble gases. You think of nobles, people who, kings and queens, people who feel like they're better than everyone else, and they don't want to mingle with anything else. Well, that's kind of what helium, neon, argon, krypton, so on do. They don't like to bond with other elements because they're already stable. And we'll talk more about that in the future. The really cool thing about these, if you look at this picture, is if we could trap these gases in a tube and send electricity through them, they make these really cool colors. You've probably seen them outside of stores, you know, like an open close sign, or even just the name of a store. Next we have group 17, which we call the halogens. The halogen group is neat because these are the things that bond with a lot of the things from over here. And you'll see why in a little bit. For example, chlorine and sodium, we know that is salt. A lot of these tend to bond together, which make very important compounds for us. But here's chlorine, one example. The light yellow in this picture is the gas form. The darker yellow is the liquid form. Chlorine was actually used as a poison in World War I, so it's a very, very powerful smelling chemical. If you have a pool, you know what chlorine smells like. Or if you've ever smelled bleach, you have an idea of what chlorine smells like. Also iodine. We think of chlorine as sanitizing. Well, iodine is often used in surgeries before the incision is made on whatever they're operating on. So it's neat how these things are used to, some of these things are used to sanitize things. So we have those. The last element that I'm going to show you is carbon. We're done labeling our groups. Those are the 4 groups that we're going to label. It's carbon. Carbon is really important to us because without it, none of us would be alive, and no living things that we can ever think of would be alive. So we are carbon-based life forms. Here's 2 versions. The one over on the left is a diamond. Most of you will either be buying one of these or be receiving one of these at some point in your life. The other form is the much cheaper version, graphite, or one of the other forms. That's what you use to write with if you have a pencil. So although they're the same thing, chemically they have a different appearance, and that can be true for a lot of these. So it's very, very cool to see how that works. Now, one of the things that we're going to do here, and you're going to need 3 different colors, is to label our 3 main sections. You notice the first is labeled metals here. Well, we're going to outline all of our metals just very, very loosely here. If you want to be a little more exact, you are welcome to, but I'm just kind of doing this freehand as I basically go across here. So if we look at these, and there we go. So if we look at these, this whole section is labeled as metals. We also have this huge grouping. Remember, I'll trace over that same arrow that's really thrown into that section. So all of these are metals. So most of the elements on the periodic table are metals. So that's something that's important to know. Also, we just change up our colors. Try to pick something different here. Here you go. We have a group called the metalloids. Now the metalloids and I'm just going to go up and over just like so. These are all metalloids, the green ones. These metalloids are not acting as metals and not acting as non-metals. They're kind of in between. If you remember silicon from the lab that we did, it could either lose 4 electrons or gain 4 electrons, which means that it can bond with a lot of things. And silicon is huge importance to each one of you, because none of your electronics, and you wouldn't be able to use any computers or anything without silicon. So the silicon chips are very important to us. Carbon also bonds with a lot of things. That's why it is one of our standards for life as we know it. And our last group, let's go to blue here, are nonmetals. But to start, we left out one over here. Hydrogen is a nonmetal. And we're just going to go down this list over to here. Oops, off that. Please try to be neater than me. These would all be nonmetals. Now you're saying, wait a minute, Mr. Leonard, you drew a red line under there. I'm also going to draw a blue line, and I'm also going to draw a green line. That's because these 3 are unknown. We can't get these in a form long enough, whether they're solid or gas or whatever, to study them and understand them in their properties, to see where they would fall as metals, metalloids, or non-metals. So these are our groups, our families, if you will, and our metals, metalloids, and nonmetals. Now the last thing that we're going to do is very simple. We've seen the periodic table before, and it gives us some information. It gives us 2 numbers, a symbol, a name, and then this up here. Well, what is that talking about? Well, that is talking, if you look at your key in your periodic table, it's just telling us that it is a solid. There's some others that are liquids, gases, and a couple other symbols that can be used. Remember, any element after 92 is artificially made by humans. Okay? So we'll start with this top number. If you remember, the top number in this example, this 11, represents the atomic number, which is really equal to our protons or electrons. Now, you probably have some space on the back of your periodic table where you can do this, or you could write it on a separate sheet. So in this case, sodium, Na, would have 11 protons and 11 electrons. So that's very simple. The second number is called our atomic weight. sometimes the mass number, and other times the atomic mass. So it has 3 different names for the same thing. It's used interchangeably. Most of the time I will use atomic weight. Most chemists will probably use mass number, but you have to know these terms. These are all telling us the same thing. They're telling us the number of protons plus the number of neutrons. So if we take a look at this example, sodium has 23 protons and neutrons added together. So one of the ways, or one of the things that we can do, is find the number of neutrons. And that's really, really easy to do. And all we have to do is take this atomic weight minus this atomic number. So in this case, if I did 23 minus 11, I would end up with 12. So in this case, sodium has 12 neutrons. I'm just going to write this over on the side. So protons, electrons, neutrons. Just to summarize, it has 11, 11, and 12. Also notice it spells the word pen. Okay, so that's an easy way to remember the 3 things that are within an atom. Okay, our last one's magnesium. We're going to go through the same process. We're going to identify how many protons, electrons, and neutrons. By the way, I should probably have a little minus sign there. That is just the symbol that we use for electrons. Okay? So in this case, since my atomic number is 12, the first 2 are very, very easy. 1, 2, they're done. The last step, remember, it's just a subtraction problem. In this case, 24 minus 12 is 12. So in this case, magnesium has 12 neutrons. Now take a note. Magnesium has 12 neutrons. So does sodium. Remember, the number of neutrons doesn't define what the atom is. That's the number of protons. So this is element number 11. This is element number 12. They're defined by the number of protons that they have. And just to remind you, we wouldn't be able to find these planets and these other stars and what they're doing unless we had a good understanding of protons, electrons, and neutrons. We can find all those things on the periodic table.